Albert Einstein's theory of relativity. Easy to understand explanation. By Nameless Saint. Albert Einstein's theory of relativity, everyone knows it, but very few understand it. Albert Einstein's theory of relativity is one of the most profound and important discoveries in the history of science. It transformed our understanding of space, time, and the nature of the universe itself. However, the theory can be difficult for non-scientists to understand, with its complex mathematical equations and abstract concepts. In this article, we will explain the theory of relativity in simple terms and provide an illustration to help clarify its ideas. The theory of relativity explained. The theory of relativity is actually two separate theories: the special theory of relativity and the general theory of relativity. The special theory of relativity deals with the relationship between space and time, while the general theory of relativity deals with the relationship between gravity and the curvature of space-time. The special theory of relativity was first published by Einstein in 1905. It introduced the idea that space and time are not separate entities but are instead interconnected, forming a four-dimensional construct known as the space-time continuum. In this continuum, time is not absolute, but is relative to the observer's motion. This means that time can appear to move slower or faster depending on the observer's speed relative to the object being observed. The special theory of relativity also introduced the concept of the speed of light being constant in all reference frames. This means that no matter how fast an observer is moving, the speed of light will always be the same. This idea challenged the traditional Newtonian view of the universe, which assumed that the laws of physics were the same for all observers. The general theory of relativity was published in 1915 and built on the ideas introduced in the special theory of relativity. It proposed that gravity is not a force that pulls objects together, but is instead a curvature of space-time caused by the presence of matter and energy. This curvature is known as the gravitational field. The general theory of relativity also predicted the phenomenon of gravitational time dilation. This means that time appears to move slower in a strong gravitational field than in a weak gravitational field. This prediction has been confirmed by numerous experiments and observations. E equals mc squared. One of the most famous equations associated with Einstein's theory of relativity is E equals mc squared. This equation shows the relationship between energy, E, and mass, m. It states that the energy of an object is equal to its mass times the speed of light squared, c squared. This equation shows that even a small amount of mass contains a tremendous amount of energy. The equation also implies that energy and mass are interchangeable, and that matter can be converted into energy. To help clarify the ideas of the theory of relativity, let's consider an illustration of a man on a train. Imagine that the man is sitting on a train that is traveling at a constant speed of 100 kilometers per hour. He is holding a ball in his hand and throws it forward at a speed of 10 kilometers per hour. To the man on the train, the ball is moving forward at a speed of 10 kilometers per hour. However, to an observer standing on the ground watching the train go by, the ball appears to be moving forward at a speed of 110 km per hour, 100 km per hour for the train speed plus 10 km per hour for the ball's speed. This is an example of how speed is relative to the observer's frame of reference. Now, imagine that the train is traveling at the speed of light, which is not possible for objects with mass, but is used here for illustrative purposes. The man on the train throws the ball forward at a speed of 10 kilometers per hour. According to the special theory of relativity, the speed of light is constant for all observers, regardless of their motion. This means that to an observer standing on the ground watching the train go by, the ball would still appear to be moving forward at the speed of light. However, this creates a paradox. In the man's reference frame on the train, the ball is moving forward at a speed of 10 kilometers per hour, but in the observer's reference frame on the ground, the ball is moving forward at the speed of light. This violates the principle of relativity, which states that the laws of physics must be the same for all observers. Einstein's theory of relativity resolved this paradox by introducing the concept of time dilation. According to the theory, time appears to move slower for observers in motion relative to observers at rest. This means that in the observer's reference frame on the ground, time appears to move slower for the man on the train. As a result, the man on the train perceives the ball as moving forward at a speed of 10 kilometers per hour, but the observer on the ground sees the ball moving forward at the speed of light. This example illustrates one of the key ideas of Einstein's theory of relativity, that time and space are not absolute, but are relative to the observer's motion. The theory has profound implications for our understanding of the universe, including the nature of space, time, and gravity. The equation E equals mc squared, which shows the relationship between energy and mass, is a fundamental component of the theory and has practical applications in fields like nuclear physics and energy production. In conclusion, the man on the train example helps to illustrate the complex ideas of Einstein's theory of relativity in a simple way. The example shows how the theory challenges traditional ideas of space, time, and motion, and introduces new concepts like time dilation and the constancy of the speed of light. While the theory may be difficult to grasp at first, it has transformed our understanding of the universe and has led to new breakthroughs in physics and other fields. You enjoy watching this video? Kindly consider subscribing to my channel. New content is posted daily. Thank you, and may God bless you.